So full title, not joke title, is To Infinity Selmer Groups, To Infinity Class Groups. Actually, before that, thank you, Raphael, for having me, and also thanks to Peter. The full title for this lecture is To Infinity Selmer Groups, To Infinity Class Groups, and Goldfelds conjecture. And for most of this talk, we're going to be focusing just on Selmer groups and the Goldfeld conjecture part of this. There's a really interesting interplay between the class group side and the Selmer group side, which was very useful when I was deriving these results. But basically, the to infinity versions are just translations of the Selmer side. If anybody cares, the thing I prove is that the two primary part of the class groups of Okay, sure. Theorem. The two primary part of the quadratic class groups, two primary parts of the class groups of quadratic imaginary fields, and then I'll just say mod genus because there's a big two-torsion part due to genus theory that I want to ignore. This behaves as predicted by the Cohen-Lenstra heuristics. And so I'm not going to detail what these are, but the Cohen-Lenstra heuristics were just a set of conjectures suggested in the early 80s, which gave sort of a guidelines for calculating the probabilities that the class group of general number fields had certain properties. And they are almost all unproven. A little bit is known for the three part of the quadratic class groups due to Davenport. A little bit more is known, much more is known about the four class group from Fouvry-Kluners. And some other number fields has a little bit of work done. For example, the two part of cubic class groups is known due to Varma and Bhargava. But mostly, these are just completely unknown, so this is actually a fairly big result in that field. But what I really care about is Goldfeld's conjecture, so I'm going to mostly talk about that. And so, more specifically than that, the problem I care most about, and which has been the motivation for a lot of my work, is the congruent number problem. So, just to recall, a positive integer is called congruent. If the elliptic curve, and I'm just going to use the notation EDC. So the dth quadratic twist of a curve I'm going to call EC. And this twist is going to have the Weierstrass form y squared equals x cubed minus d squared x. We call D congruent if this curve has positive rank. Or to put it in another way, it has a non-trivial point that is a point other than infinity, 0, 0, d0, and negative d0. This is a decidedly modern formulation for this problem, which dates back, I think, about 1,000 years. In the previous formulation, congruent numbers were known as the area of right triangles with rational side lengths. So 6 is a congruent number from the 3, 4, 5 triangle. And since their invention about 1,000 years ago, congruent numbers have really been a benchmark of progress on elliptic curves. For example, the first descent done by Fermat was figuring out that 1 wasn't congruent. The first use of Heegner points was proving a bunch of primes were congruent. Tunnel's theorem is one of the major results by Tunnel, and it gives you a solid criteria for figuring out if something is congruent based on the Birchon-Swinnerton-Dyer conjecture. So this is a very important problem within the study of elliptic curves. But not a lot is really known about it. When you study the distribution of congruent numbers, you'll notice something immediately. And it's that the situation varies a lot depending on whether D is congruent to 1, 2, or 3 mod 8 versus when it's congruent to 5, 6, or 7 mod 8. And what you'll notice is that almost none of these actually are congruent numbers, whereas all of the D congruent to 5, 6, or 7 mod 8 are. And so this comes from the analytic number theory underlying the situation. If you compute the global root number for EDC with D congruent to 1, 2, or 3 mod 8, what you find is that this root number is always going to be plus 1. And in the other case, the root number is always minus 1. And the root number gives you the sign for the functional equation of the L function associated to this elliptic curve. So when the root number is plus 1, that implies that the analytic rank of the elliptic curve is always even. When it's minus 1, the analytic rank is always odd. So even. OK. And so in particular, if we assume the Burton-Swinnerton-Dyer conjecture, the fact that the analytic rank is odd in this case suggests that the actual rank should be odd. And that means that the actual rank, which is one of 1, 3, 5, 7, whatever, and so is always positive. So if we assume the BSD conjecture, we get that for 5, 6, 7 mod 8, we have all are congruent. Oops. OK. Whereas, OK, the other case is a little bit more mysterious because the analytic rank could be 0, in which case it's not congruent, or the rank could be 2, 4, 6, 8, whatever, in which case it is congruent. And so what's the distribution there? But fortunately, we do have a heuristic for understanding that, and it's Goldfeld's conjecture. And Goldfeld's conjecture more or less says that the rank is almost always as small as possible. So in this case, the rank is almost always going to be 0. So we have 100% rank 0 conjectured. So 0% are congruent. Whereas in the other case, Goldfeld's conjecture tells us that 100% should have rank exactly 1. OK. So this is what's conjectured. But very little was known about these conjectures. Sadly, I overestimated how much table space I had. So we'll just go on to the next board. Let's line these up. And so previously, the best results known on this, basically until a couple of years ago, were due to Heath Brown. And what Heath Brown figured out is that at least 40% for D congruent to 1, 2, or 3 mod 8 have rank at least 0. So this is Heath Brown. And using the same argument, he was able to show that greater than or equal to 80% had rank less than or equal to 1. And so until about 2015, these were like the only percentages that were known. Since then, we've improved. This bound was improved a little bit. Now we know that at least 50% have rank exactly 1. This is a Heegner point computation that I did based on work of Tian Yuan Zhang. And it's why I'm interested in this problem to begin with. I was able to do like the last matrix calculation to understand the Tian Yuan Zhang condition. I proved that 50% had rank 1, and I was like, OK, what other percentages can I improve in this picture? And the answer is you can improve all of them. And in fact, the new results are that this prediction is correct. So we now know that 100% of D congruent to 1, 2, and 3 mod 8 are not congruent numbers. And similarly, we know that 100% of D congruent to 5, 6, or 7 mod 8 have rank less than or equal to 1. So if we assume the BSD conjecture, we get Goldfeld's conjecture. And so to me, this is my main result. This is the thing that I'm most proud of, the fact that I proved that almost none of the D congruent to 1, 2, or 3 mod 8 are congruent numbers. But
so when you less equal than 1, that 2, so even Selmer group doesn't tell you the rank is 0 or 1, right?
no, it doesn't. What we do know, spoilers, is that the 2 infinity Selmer rank in this case is exactly 1, 100% of the time. But because we don't have the parity conjecture or BSD or anything like that, we can't translate to rank 1. I'm hopeful that something like a Skinner or Bong kind of thing can come along and sweep in with the 2 infinity Selmer rank and get out an actual analytic rank. But
Converse.
yeah, converse. Wait.
B equals 2 is that?
Yeah, probably not. Be nice though. Okay. But this is really a corollary of my main result, which has to do with the distribution of 2 infinity Selmer ranks. And so for that reason, I'm going to talk a little bit. I'm going to have to give a little bit of notation just to understand first Heath Brown's work and then how I built on top of it. So notation. Just the briefest review of Selmer groups. We define the end Selmer group of an elliptic curve to be a certain module cut out by local conditions inside the set of cocycles, Galois cocycles, in the end torsion of E. So here GQ is the absolute Galois group of Q. And what's important about the Selmer group is A, that it's finite, so it gives us good bounds on the rank of the, so we can find bounds on its size. And second, there's a natural inclusion of EQ mod NEQ into the Selmer group. Okay, so using this, I'm going to define the notion of an n Selmer rank. So we're going to call the n Selmer rank of E. That's going to be the maximal R, so that Z over NZ to the R embeds into the n Selmer group of E. So how many copies of Z over NZ can we fit in? And this is a useful thing to have because due to this inclusion, we always know that the actual rank has the n Selmer rank for any n as an upper bound. So if we can bound the n Selmer rank, then we have a bound on the rank as well. And so that's exactly what Heath Brown did, and later what Kane would do for a slightly more general class of curves, is they figured out the 2 Selmer rank bounds. They figured out the distribution of 2 Selmer ranks, and thus the corresponding rank bounds. To understand their distributions, I'm going to define one probability that's important, which is something I'm going to call P alt nj. And this is the probability a uniformly selected n by n alternating matrix with coefficients in F2 has nullity J. So here, alternating means that the alternating F2 matrix, that's a matrix with zeros along the diagonal, which is symmetric off the diagonal, where all entries are either 0 or 1. And importantly, this is always going to be 0 unless n and j have the same parity, as the rank of an alternating matrix is always going to be even.
J means the rank n minus j?
Yeah, so this would be rank n minus j, which is nullity j, so dimension. I believe. Nullity is one of those words that shouldn't exist, but I'm using it here. Final piece of notation, and I'm only using it because it comes up a lot, is I'm going to use square brackets around n just for the set of natural numbers 1 through n. Okay. Best way to do this, yeah. So first, the theorem of Kane. So Kane was able to extend what Heath Brown would do for the congruent number curve to a slightly more general set of curves that I'm going to say satisfy star. So take E over Q satisfying star, where star is the condition first that E has full rational two-torsion. And second, that E has no cyclic 4 isogeny defined over Q. OK, going through these conditions, this one is a huge condition which gets rid of almost all elliptic curves and without which we can do nothing. And this is a stupid condition that comes because nobody felt like doing the extra casework required to get rid of it. And that's been true since about 2005 when Swinnerton-Dyer started thinking about this stuff. So given an elliptic curve satisfying these two conditions, then as we take larger and larger quadratic twist families.
What did Swinnerton-Dyer do that Heath Brown had not done? Did he just look at more general E's?
Yeah, he looked at more general E's. He sort of did an orthogonal thing to what basically Swinnerton-Dyer plus Kane is bigger than is a generalization of Heath Brown. But Swinnerton-Dyer by himself did not generalize Heath Brown. He had to assume all sorts of things.
But he wanted to look more general.
What do you say? Yeah, he was setting up.
Congruent curve, it was nothing.
It was already known for the congruent curve, but for all the other curves satisfying star, it was a new idea. Basically, just more careful work with the matrices set up by Tate, I think. So as we take larger and larger quadratic twist families, the proportion of quadratic twists such that ED has a 2 Selmer rank j plus 2. Here we're just assuming that j is greater than or equal to 0. So the proportion of such things is equal to 1/2 of the limit as n goes to infinity that in alternating matrix, oh no, I have to get rid of the beginning of my table. A random matrix with 2n plus j columns has nullity exactly j. OK, and so a couple things about this. First, the reason we need a half here is because half of these, if we just had n going to infinity, half of these matrices, half of these values would be 0. And so we need to basically average that out. And so to do that, we fix the parity and take half.
And random here means each entry is 0 or 1 with probability of half.
Yep, that's exactly what I mean. There's two n squared minus n over 2 possibilities, and you choose each of them with equal probability. OK. And so this is what they, and the other thing I'm going to note about this is there's a mismatch between the nullity, j, and the 2 Selmer rank j plus 2. But this comes from the fact that the minimal 2 Selmer rank for such a curve is always going to be 2. Because when we look at this group, we have the bit coming from the full 2 torsion. So in particular, among D congruent to 1, 2, or 3 mod 8, we find that the 2 Selmer rank of the congruent number curve twisted by D is going to equal 2 about 41.8% of the time. And so since this is the minimal 2 Selmer rank, this implies that the actual rank is equal to 0, at least for 41.8% of the time. And so by doing this 2 Selmer calculation, they were able to get the old results, the old best results for the number of curves with rank 0, and also similarly, starting with 5, 6, 7, you get rank 1. Okay.
This is Kane building off of Swinnerton-Dyer?
This is Kane building off of Swinnerton-Dyer, with both of them building off of Heath Brown. I think Heath Brown gets most of the pie, then Kane gets like a third of the pie. So the question I had was, how can you generalize this? We have now these statistics for the two Selmer groups. How can we extend these to statistics for the to more general statistics that would allow us to prove better bounds? And the answer is to make this bigger. So we see that the 4 Selmer rank is always going to be less than or equal to the 2 Selmer rank. The 8 Selmer rank is always going to be less than or equal to the 4 Selmer rank, so on and so on. And so you get finer and finer invariance. And if the Tate-Shafarevich conjecture is true, then we expect that eventually those invariants will actually bottom out at the actual rank. So if we can just figure out the distribution of 2 of the k Selmer groups for all k, then we have a way of we'd have a way of proving that 100% had rank 0, or finding the actual rank statistics. And so that's exactly what I did. And the main theorem is the following. So take m greater than 1 and choose a sequence of integers n1 through nm that are decreasing and non-negative of the same parity. Also choose an elliptic curve e over q satisfying star. So this is the input. Define 2 sets. Take wk to be the subset of natural numbers, so that for j less than or equal to k, the 2 to the j Selmer rank of the twist of E by D is equal to nj. So with this, we see that W2 is a subset of W1, so on and so forth. And what we really want to do is we want to figure out the size of Wn relative to n. And the actual result is a transition. So then, as we take larger and larger subsets of these groups, the intersection of the first n natural numbers with Wm, intersected over Wn minus 1. So this is a subset of this, and we say that the relative size of these is equal to the probability that a random matrix with nm plus 1 rows, nm minus 1 in rows, has a rank nullity exactly nm. And I think, oh no, I'm good. Okay, I was worried that I forgot the 2 again, but this is fine.
So these numbers that determine the group structure, right?
Yes, this exactly determines the group structure, because by using these in succession, we essentially get a Markov process that describes the infinity Selmer groups. We start with something, we use Kane's theorem to figure out the initial state, the n1, and then these give us transition probabilities that give us a chance of going from nm minus 1 to nm for any given nm. And so this is super nice because it fully describes the 2 primary part of the Selmer group, and this is exactly what's predicted by any of the heuristics that we have, Bhargava, Kane, Lenstra, Punin, Rains, more recent, and Delaunay originally. And yeah, the other thing that's really good about this.
I saw Lenstra quite recently before your paper.
What do you say?
The one thing he doesn't believe is the 2 part of his conjecture.
Oh man, that's so nice to know, because when I proved the 2 to the k case, the thought that was going through my mind is, oh, good for me. I proved baby Cohen-Lenstra. Oh well. Like this is the.
It's the closest to structure, so it's the reason that it's going to be subtle. And so he was quite nervous. He said he may have. There's some extension which he seemed to claim that he's very skeptical about. But anyway, I'm just.
I'd fully believe that. There might even be problems with real quadratic fields.
Right. Maybe that's what he's saying.
Yeah, the units might add a wrench to the system. Similarly, if you look at things without full 2 torsion, you get all sorts of hiccups that disagree with Bargava-Kane-Lentre-Punin reigns. But we don't have to deal with those because I assumed star. Okay, good. And so let me just check where I'm at. And so obviously this is an extension of the work that was done by Kane and Heath Brown before me. Basically, I was using their work as a base case to understand something more general. And so what I'm going to talk about now is why star is so important to this, or why we need to assume it so substantially. Actually, first, I'm going to give the punchline, because the main reason I cared about this was to prove things about the congruent numbers. And so what you find is that if you sum up all these probabilities with nm not equal to 0, you get something that's always bounded by 2/3 or so. And so the probability that 0 or 1, I should say, because of parity. So the probability that you end up in a state other than 0 or 1 after k steps is exponentially decreasing with k. And so using that fact, we get our happy corollary, which is so for E over Q satisfying star, we have that the proportion, I shouldn't make this another limit, as n goes to infinity, that's not even necessary. Okay. We have that the size, or the number of d, less than or equal to n, with ed of to infinity Selmer rank greater than or equal to 2. The size of this set is going to be little o of n. So that's enough to say that this set is 0 density. What we haven't done is we haven't proved a really sharp bound for this little o of n. If you look at our work, the best little o, the little o of n we expect is n to the 3/4 plus epsilon. So that's what's conjectured. That's what all the heuristics suggest should be the case. And whereas by trying our very best, we get n over log, 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 n to the 1/3. Which is phenomenal progress. Okay, cool. So
Your methods, if I restricted D to be in numbers which are at most 20 prime factors, you don't know how to prove that case. Right?
What do you say?
Really need, I mean, I'm just making clear something that we discussed earlier.
yeah, so
You heavily will be using the fact that your D's have many unbounded, growing number of prime factors.
yeah, not only a growing number of prime factors, but likely to be, we need the prime factors to be equidistributed if we take their logs in the right way. Because
I'm saying these conjectures are probably still true of, this minimal statement is probably true even if you go through these, which are
yeah, even if you vary one prime factor, I would expect that these conjectures are still true. But I'll mention why in a little bit that I'm a little skeptical that we'll ever get, that we'll get using methods like these results for those cases.
I got stuck in that problem.
Yeah, Red Eye got stuck in this problem at 8. So he was able to figure out the 8 class group, which was a surprise to many mathematicians even recently, that he had gotten even that far. but 16 is the domain of recent work of Iwaniak, Mazer, Rubin, and I forgot someone.
Now Milovic.
Yes. What? Oh, actually, I was thinking thinking the original. Yeah, the original spin paper, and then more recently Georgia Milovic, and all of those rely on the spin of prime ideals, and that is an invariant which is very bad for this sort of stuff. It's much harder to deal with and to prove things about. And once you get to 32, nobody knows any way of dealing with single prime families. There's just no invariance known. Okay, cool. So this is what we want to figure out. And so the first step to understanding this is to really understand why star is so useful. And so I'm going to define some more notation. And bear with me for this piece of notation because it looks just a little silly. We're going to, for delta, a unit in the rational numbers, and T, a subset of R, so the first R natural numbers. We're going to define the quadratic character associated with delta T on a set of primes P1 through PR to be the quadratic character associated to Q root delta times the product over T of Pi. So this is a function which takes in R primes. So for any given delta T, chi delta T is a function that takes in R primes and spits out a quadratic character. Okay. And so the reason we care about quadratic characters is because since we have star, we have this isomorphism between the 2 torsion and z over 2z squared. And that gives us an isomorphism between this Galois cohomology group and 2 copies of H1GQ z over 2. Okay. And so, why? Okay. And so between this isomorphism and this construction, we can think of a quadruple T1, T2, delta 1, delta 2, applied to P1 through PR as lying in the set of the Galois cohomology of GQ, E twisted by P1 through PR 2. So the recipe here is we take T1 and delta 1, we apply chi delta T to it, we apply P1 PR through that. That gives us our first quadratic character, And then similarly, T1 delta 2, or T2 delta 2 gives us a quadratic character in here. We apply P1 through PR, and that gives us the second one. And so the reason this is useful is because it allows us a way to understand preserved Selmer structure between different quadratic twists. So first proposition, and this is very easy, is if T1, T2, let me not write that, all 2 Selmer elements of E twisted by P1 through PR are represented by a tuple with delta 1 and delta 2 dividing the 2 times the conductor of E. And so delta 1 and delta 2 have our worst places, the ones that are ramified in our original elliptic curve. For example, for the congruent number curve, it would just be 2. And otherwise, all the ramification comes from indices T1, T2. So that's very basic. The other thing that's wonderful news is we have this theorem of classical descent. Let's see if I can fit this. We can determine if our tuple, which I'll just call W, so W is the 4 tuple, we can determine if W of P1 through PR is in the 2 Selmer group associated to EP1 through PR. Sorry that this is getting so cramped over here. But we can determine if our tuple at P1 through PR is in the 2 Selmer group of P1 through PR just from first the PI mod 8 times the conductor of E, and 2 the Legendre symbols. Pardon?
That's his matrix. Matrix that has like Siri covering.
Yeah, exactly. This using this information, you can define the Rede matrix or the Monsky matrix or some variant of that. And what do you say?
It's Red-Eye. Who's Monsky?
Red-Eye did it for the 4 class group. For the 2 Selmer group.
For the sum.
Yeah, the 2 Selmer case is handled by Monsky. And the congruent number case, and by Swinnerton, Dyer, or let's just say Fermat. Fermat's in on this a little bit.
I think Red-Eye, as you said earlier, his work was not appreciated, I think, in many circles, because he kind of was doing this analytic thing using class field theory, and at that time, those subjects were completely disjointed.
Yeah, that's more people should read his papers from the 30s.
I think he's from the Hesse school, Red-Eye.
Yes.
Hungarian.
It's a little hard to understand his class field theory nowadays, now that we're all spoiled by Tate and such. But yeah, no, there's a lot there. So this is mostly due to Red-Eye, partially due to Monsky and others who just filled in the details for elliptic curves, which should be understood as just completely analogous objects. Okay, and so this is extremely useful. And the reason it's extremely useful is because it allows us a way to understand this 2 Selmer structure between curves. So the first big step, well, by some counting, in my proof, is to restrict from D inside of just all the integers less than n to points, let's call them x, equal to the tuple P1 through PR inside some product space x1 times ... through xr. Where the 2 Selmer structure of E twisted by all the primes in a little x does not depend on little x. Okay, and so this step is a huge pain. Because in this step, we need all of the matrix of Legendre symbols to all be the same for every point in the space. We need pi mod 8 times the conductor to be all the same. So in order to get this done, you need either Riemann hypothesis, or you need the large sieve plus Chebytarov density, and a little bit of combinatorics. And using that, you're able to shave down n to a space where this is true.
Riemann is obvious.
What do you say?
What's the combinatoric?
Okay, yeah. So the specific issue that comes up is when you're doing the shaving, you can't get rid of all the small primes. So the pi, pj over here, they form a matrix. So let's say p1 less than p2 less than p3 dot 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 to pr, and then p1 again dot 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 to pr. We get this big matrix. And most of the symbols we can understand really well using Chebytarov and large sieve, or to join those up, the Riemann hypothesis. So if we assume the Riemann hypothesis or do a lot of work, we can deal with everything outside of a small corner in the upper left-hand side. And by small, I mean much smaller than this picture would suggest. You can control everything outside of a number of indices.
To be precise, the Chebytarov is telling you that this is looking like a random matrix at the scale outside that small box.
Yes.
By just using Chebytarov, while in the box you don't know anything.
Exactly. Yes. So we have to deal with this little box of small primes being bad with each other. And so the way we get rid of this is, since we only really care about the two Selmer structure, we don't need these primes to be in order. So once we prove all of this is equidistributed, it doesn't matter what this is. It could be 0, 1, 0, 1, 0, 1. What we do is we permute the primes and get a different red-eye matrix. And by considering that over all permutations, we can mix in this fixed stuff with the rest, and we get something that looks like an arbitrary matrix, or a uniformly selected matrix with certain fudge factors.
So what's the scale of this small point?
Oh yeah, it's logarithmic in R. So so what I actually need is I need a sort of Nomis shape of badness, or that's what I use in my argument. And so with the Nomis shape of badness, call this part R0, so this size is R0, this is R1. Then what I need is 2 R0 times R1 squared. What do you say?
What's the word you're using?
Nomis. It's an L shape. That's a thing, right? We need 2 R0 R1 squared to be much less than R0. If that's true, then this mixing argument goes through. If it's not true, bupkis. Okay. Cool.
Much less than R?
What do you say?
Much less than R.
Yeah, sorry. This is the notation I actually use, so I get a little confused when I have just R's floating around in the talk. Okay, cool. So this is the first step. And now, what should we do for the, so the next question I want to ask is, why do we expect, why is it supernatural for these to be alternating? Why do we expect these alternating probabilities to show up? And the answer is they come directly from, did I take a whole board to write my main theorem? Yes. They come from the Cassels-Tate pairing, which is an alternating pairing defined on the Selmer group. And so I'm just going to write this up. The proposition, do the Cassels and Tate, is choose E over Q. Just any elliptic curve, don't need star, and k greater than 0. Then there is a natural bilinear alternating pairing going from the 2 to the k minus 1 divisible part of the 2 to the 2 Selmer group, which is just the 2 to the k Selmer group times 2 to the k minus 1 with itself, obviously, mapping to F2 with kernel 2 to the k times the Selmer group, the 2 to the k plus 1 Selmer group of E, plus torsion, because torsion just is terrible. So we have to add this to the kernel, but in all applications, this doesn't actually matter. OK, so this is a naturally defined thing that we don't know a lot about. But let's try to apply this to the situation described here. Take a look at an element inside of Wn minus 1. So a d in Wn minus 1. That's going to be something with 2 to the m minus 1 Selmer rank equal to nm minus 1. And so that means that if we set k equal to m minus 1, this is going to be an F2 vector space with dimension nm minus 1. So we have a pairing defined on an nm minus 1 vector space with coefficients in F2 that's bilinear and alternating. And so what this is suggesting is if these pairings are equidistributed among all possible alternating pairings of this form, then this actually pops out. Because what this is saying is if this is a pairing on nm minus 1, if this is an nm minus 1 dimensional pairing, then the nullity of this is exactly equal to the rank of the to the k plus 1 Selmer group. So the thing we actually want to prove then is that this Castle-State pairing is equidistributed among all possible options. And so this is why it was super important to set up this tuple system. Because before we had the tuple system, we had no way of comparing the 2 Selmer group of one twist with the 2 Selmer group of another. And so it didn't make sense to say the matrices here are equidistributed. But now, from this first step, we have a big grid X on which all the 2 Selmer groups are exactly identical and so we actually can say, yes, in a sensical way, the Castle-State pairing at each level are equidistributed on this grid. And so that's a huge step. Now, the next question is, OK, what do we do from here? How do we actually prove this is equidistributed? And the first guess is, oh, maybe there's some extra information that we can use, like this, that will give us what the 2 to the k Selmer group is at any given point, or at least what the Castle-State pairing is at any given point. But no, definitely not. It's possible for the 4 Selmer group, and this was actually an original calculation I did. You can find the 4 Selmer group at any given point without too much trouble. But you can't do it in a way that doesn't require a Riemann hypothesis, and there's no extension beyond that. As soon as you have the 8 Selmer group, you need to deal with the spin of prime ideals, which we can't. So that doesn't look super useful. But, oops.
That comment is supposed to be about this mother group that controls it.
What do you say?
When you say spin of prime ideals, you mean there's no description so that the prime problem that you need to deal with is an ordinary multiplicative function.
Yeah. So that's the way that you.
I'm just checking that you're referring to this Milowich thing that 16 is where it stops.
Yes, that's exactly right. 16 is where it has already stopped. Like, you can't do 16.
He did 16 with the spin.
Yeah, the point is that Shebetarov can't give you equidistribution if you try to apply it to points because there isn't a good enough field theoretic description. So that looks bad. But we have one general principle which allows us to do everything. And that's the fact that we don't actually need to prove anything about individual points. We just need to be able to compare points. And so here's the simplified principle. Suppose we know the 2 to the k Selmer structure at all but one point in a k plus 1 dimensional cube. I guess I should say hypercube, in our product space, which I think I called X. I did not. Nuts. In our product space. So by this, I mean a cube is a selection of 2 primes inside of each of these sets, or inside of exactly k plus 1 of these sets, and 1 prime in all the others. So that gives you a total of 2 to the k plus 1 possible twists. For all but one of those, I'm saying that we know what the 2 to the k Selmer structure is. So we just need to figure out the 2 to the k Selmer structure of the one remaining point. Then the last 2 to the k Selmer structure can be determined by the splitting of PR in some field generated from the description of the elliptic curve and the primes P1 through PR minus 1. So using, we don't have a number theoretic condition to describe the 2 to the k Selmer group at any given point. But if we have a bunch of information already, we can use it plus some splitting information to get the next point. And so suddenly the use of Chebytarov has changed a lot. Where before Chebytarov was used to prove equidistribution in itself, all this is doing is we're using it to inject some randomness into our grid. So since Chebytarov says that basically any symbol is equally likely to be anything, if we get a full grid of them, then suddenly we have a lot more information. And so
what's the field? It's like the governing field here. Say it again.
I did not say.
Yeah, you used it.
The governing field is a 2 solvable extension. That's all I got. It's defined to be only ramified at a couple of the primes, so it's small enough to do Chebytarov too.
Yeah, you have to control it.
What do you say?
You control the degree.
Yes, yeah, the degree of this is controlled. What it looks like, it is not abelian, so you have something interesting. It's a generalization of the dihedral. Dihedral groups are the first case that comes up. So in order to control the 4-class group, you need to understand, or not the 4-class group, the 16-class, the 8-class group, you need to understand dihedral extensions. And then to understand the 16-class group, you need to understand a certain quadratic extension of the dihedral extension, et cetera, et cetera, et cetera. Not a quadratic. I think it's degree 32 or something. Yeah. OK, so first I'm going to explain why the simplified principle is useful. And to understand this, suppose we have.
Easy, or the simplified principle? Is that easy to prove?
No, it's very hard. What do you say?
So how's it simplified? What's like the
Oh,
No, it works.
it doesn't work like that. It's simplified in the sense of you need a billion conditions on the 2 to the k Selmer structure. And I'll get into that a little bit for about exactly 2 minutes. So the first thing I'm going to talk about for 2 minutes is suppose we have a big grid. OK. We have a big grid, basically a big chessboard. And we fill in all of the entries to be 0. So big grid, all entries 0. And suppose you wanted to label the vertices so that the sum of the vertices around any given cell sum to the cell mod 2. So for example, in this upper hand corner, we could put 1, 1, 1, 1. And those would sum to 4, so 0. And so if all of these cells are 0, what's the minimal number of ones we require to do this? This is a trick question. 0. We can do it labeling only with zeros. So we can label all the vertices zeros, and it's fine. That doesn't matter. What's the maximal number of ones we could use? All of them. Yeah, so we could fill the vertices with either all zeros or all ones, so we have no control at all on the distribution of the function on these vertices. However, if instead of filling the cells with zeros, we filled them with some random function, suddenly this is much harder. And if the grid is large enough and we choose a generic function for those cells, then it turns out that the number of ones put on the vertices is going to be between half minus epsilon of them and half plus epsilon of them. And so that's a huge statistical tool. When we generalize this to larger grids and larger grids, that's what we end up using. So we use Chebotarev to fill in the cells and prove that they look generic most of the time. And then from that, we say that, OK, that means that we can't label the vertices in such a way that we have anything other than equidistribution. OK, so that's the main idea. And I have 3 minutes, which is actually enough time, just to give notation for just a sense of why the simplified principle is true. And so this is going to get a little more general than the rest of the talk has been, or a little more abstract, I should say. So take M to be a 2 infinity torsion, a GQ module, so Galois module. And take chi1 through chi-r to be quadratic characters. For S a subset of 1 through r, we're going to take ms to be m twisted by the quadratic characters in S. And we're also going to define a non-equivariant map, beta S, that goes from ms to m. OK, so now all the objects we care about, Selmer elements, class elements, can be described using cocycles inside twists of these forms. So take a psi S inside of H1 GQ MS. OK, for each S. And so the dumb idea I had once upon a time was, hey, so this is a 8 Selmer element or something. Let's just use beta S and turn it into a Selmer element somewhere else. And that does not work at all. And the reason it doesn't work is once you use this non-equivariant map, you change the coboundary to something that's not 0. So that's too bad. But we have an inductive process for making this work a little. So under the stringent requirements that the sum, so suppose that for each index, we have that the sum across all S that contain I of beta S psi S multiplied by 2 is equal to the 2 times the sum over all S not containing I is equal to 0. OK, so this is basically saying we have a cube, a hypercube of modules here. And if you sum up the psi S corresponding to any side and multiply by 2, you get 0. Then the sum over all S, so yeah, over all S of beta S psi S, this time without a 2, well, we don't necessarily know that it's 0. We do know that it is going to be a cocycle. And so we can do linear algebra to it to manipulate it. And this is actually the first part of the simplified principle. Yeah. And so that's all I've got.